Welcome to the Walton Pi. The video you are about to see is a test review for a math proofs class. We talked about functions, injections, surjections, and bijections, and how they relate to cardinalities. We also went through some examples of using the Schroder-Bernstein theorem and the Barber set in order to show that different sets have different cardinalities, and then we went through several examples together. Enjoy. Okay, let's get started. Does anyone have any questions that they would like to go over for your test coming up? Feel free to either speak up and say it or send me a question in the chat. Both of those will work out great.
I have one.
Yeah.
So I haven't been quite able to understand in our first section that we're supposed to be studying 24 with the modules with Z. I can't figure out how we're supposed to prove that with functions. And I have an example.
Okay.
Did you want me to share my screen or something?
Go ahead and just read it out and I can do that. Or if it's a problem in the book, I can pull it up and we can write it down that way.
It is a problem in the book.
Okay. So it's integers modulo n, or is that the one right after that one? Oh, it's 24 you said?
Yeah, 24 number 3.
Okay. So that one, let's pull that one up. So that is where we have A is finite. That's a little big. All right, so A is a finite set and B is any set. And then we are looking at f defined from A to B is a function. And then consider f as a set of ordered pairs. Conclude that that means that the cardinality of f is equal to the cardinality of A. Is that the problem you're thinking of?
No, I'm trying to find it, sorry.
Okay, you're good.
It's 25 number 3, sorry.
25 number 3. Okay, not a problem. Okay. So that one is, we have a function from the integers mod 5 to the integers mod 5 defined by f of the class of A is equal to the class of 2A plus 3. And we are trying to prove that f is well-defined, injective, and surjective. Okay. So to start by proving that something is well-defined, that is proving that f is a function and not just a relation. Because a relation, you can have the same element mapped to multiple points. In a function, every element has to map to exactly one point. And anytime we are dealing with the integers mod 5, there's a bunch of different ways to write the same value every single time. So, for example, the class of 1 is equal to the class of 6 is equal to the class of 121, and so on. To show it's well-defined, we have to show that it doesn't matter which one of these we put in, it's always going to give the same output. So that's what it's going to be trying to get us to show for the well-definedness. So to start, we're going to start by assuming, so let's write down what we're doing. So this is well-defined. So that's where we are going to assume that we have two different ways to write the same thing. Which tells us that that means that we can probably write B as being A plus 5 times K. And by probably, I mean definitely, because this is how two elements in the same class are defined. So we can write B as A plus 5 times some integer K. And so now we're going to be looking to see what happens if we look at f of A and f of B. So we have f of A is equal to the class of 2A plus 3. And we now need to show that f of the class of B can also be written that way. So that's going to be the class of 2b plus 3, which when we substitute in b equals a plus 5k, that gives us a 2 times a plus 5k plus 3, which is a 2a plus 5 times 2k plus 3. And this 5 plus 2k can kind of be pulled to the side, so we get a 2a plus 3 plus 5 times 2k. And the nice thing about adding things mod 5 is we are defined that we can break it up by addition. So this 5 plus 2k is what's left over, which can then be simplified as being a 2a plus 3 plus the class of 0, because the class of 5 times an integer is the class of 0. And so that is our proof of it being well defined. The next thing we have to do is we have to figure out, is this going to be injective and surjective? And so injective is kind of going the other way around. We're starting by assuming that f of a equals f of b. So if we were to do that one, let's get that one real quick. So that's where we would start by assuming that f of the class of a equals f of the class of b. And now we have to show that that means that the class of a equals the class of b. So if we look at just what those classes are, that's the class of 2a plus 3 is equal to the class of 2b plus 3. And again, we can break this up by addition. So we get a class of 2a plus the class of 3 equals the class of 2b plus the class of 3. And the nice thing about adding is we can add the multiplicative inverses, so we can add the class of negative 3, so that just gives us the class of 2 times the class of a equals the class of 2 times the class of b. And here we might want to try and just divide by 2. The problem is division is not allowed in the integers mod n. You are not allowed to divide by anything. You're able to add, you're able to subtract, and you're able to multiply, but you're not allowed to divide because sometimes it doesn't work out. And so instead what we have to do is we have to see, is there a number that we can multiply by 2 to get 1 in z mod 5? So we look to see, is there any number we can multiply by 2 to get something 1 bigger than a multiple of 5? And it turns out that the class of 3 works out very nicely. So we're going to multiply both sides by the class of 3, and that's how we can simplify down to the class of 1 equals the class of b. Does that make sense to everyone? Does anyone have any questions as to why we have to multiply by 3 instead of dividing by 2? Okay. So that's how we would show it is injective. Let's go through and do surjective then. So to start by surjective, we're going to start by picking something in the class, or in z mod 5. So let's pick b is an element of z mod 5. We now need to find an a that's going to send f of a equals, so we're going to be looking for an f of the class of a equals and trying to get it to be equal to b. So let's do some scratch work to figure out what that's going to have to be. And so our scratch work is going to be, we start by just setting 2a plus 3 equals the class of b, and now we solve for the class of a, and see if we're able to successfully do that. So we can subtract the class of 3 from both sides, so we get the class of 2 times the class of a equals the class of b minus 3, which is the same thing as writing the class of b plus 2. Both of those are the same. The next thing we can do is we can try and cancel out our 3, or our class of 2, by multiplying both sides by the class of 3 again. And so what that's going to give us is that gives us equals 1 times the class of A is equal to 3 times B plus 3 times 2, which is equal to the class of 3B plus 1. So we're going to go over to our proof and say, let A equal the class of 3B plus 1. And now we're going to just plug that in, and through doing some work, you should be able to conclude that is going to be equal to the class of B. Does that make sense as to how that works for everyone? Does anyone have questions with that? Did that answer your question?
Yeah.
Cool. Any other questions that people have or would like to go over?
Yeah, actually, I was looking at this section and the part or question 6 in this one as well.
Okay.
I did it a while ago and I got to an answer and it worked, but I was wondering if there's like an easier way.
So we have is from z squared to z, where f of the pair m comma n is equal to 3m minus 2n. And we're trying to tell if this is injective or surjective. So the first off is we need to figure out, is this going to be injective? So is there only one way to get a given output? So if we have, for example, let's just pick a number. So let's say that we have f of AB is equal to 5, which is also equal to f of mn. Is there only one way to get 5 out from this particular problem? Well, let's see if we can come up with one way to get 5. So one way is to have a 9 minus 4, so that would be where m equals, not m, on this side this is a, so that would be where a equals 3 and b equals 2. That's one way to get it, but we could also get it by having m equals 5 and n equals 5, because then we get a 15 minus 10. So there's two different ways to get the same output. And so because we have two different ways to do it, this tells us that this is not injective. The next question is surjective, so we have to figure out, is there always a way to get a given output? Now, what you might notice is we wanted to get out 5, and if we just pick both inputs to be 5, we got 5 out. So the question might be, if we have something where we are saying that we want to get the output B, so we want to get B out. Oh, this isn't a class. I don't need the bar over it. So if we want to get B out from our function, is this always going to be equal to f of b comma b? Well, that's going to be equal to 3b minus 2b, which is always equal to b. So if you want to get b out, just put b in twice into your function, and you will always get b out from your function, which tells us that this is surjective. Does that make sense?
Yeah, that makes sense. I did it a lot more difficult of a way, so that helps.
Like, there are other ways to go about doing it. Like, you could show that you can always get 1 from various values of m and n and generate them from there. This isn't the only way to do it, but this function would be surjective and not injective.
Yeah, that makes sense. I think I did because 3 and 2 are relatively prime. So, Okay. Thank you.
You're welcome. Any other questions about this? Or any other questions that people have? Let's see, so do you feel comfortable using the Schroder-Bernstein theorem then on being able to show two sets have the same cardinality?
Well, in summary, if I understand it correctly, just find an injective function from one into the other and vice versa.
Yeah, if you have two sets, like you have this set A and you have this other set B, if you can find one injective function f from A to B and a different injective function going the other way, if there's an injection going both directions, then their cardinalities are the same. So it's a super simple concept, but as I'm guessing you saw, the proof is somewhat tedious to get through. But yeah, if you can find an injection both ways, that does make it easier to show that that means that there exists a bijection, but it doesn't necessarily tell you what that bijection is. So that's the
Do
way
we have to
show.
remember like do we have to remember like the entire proof for the Schroder-Bernstein?
I don't think so. If you want, I do have a video that I've made on the entire proof, where I go through all four of the cases. Because what you can do is you can kind of break these problems up into two sort of situations. So you have one set here, and you have another set here. The different ways that you could have your chains, or you could have these sort of like constantly going back and forth loops that eventually start and end at the same point. And so that's going to create one partition or one piece of the two sets. And so you define a bijection on that piece. Then there's a couple other cases that you could have. You could have these infinite chains that just never, ever, ever repeat. So that's going to be one case that you would have to define a bijection on. And then the other ones are, there is some initial point in B or some initial point in A, after which everything then goes on for an infinite chain from then on. Those are also going to be your other situations that you deal with. So you can, if you can remember to break it up into those four cases, then all that's left is to figure out what bijection do I define on each of those pieces. It can be a bit complicated and tedious to figure out what those bijections are, but there is always going to be a bijection that you can define on those using the fact that F goes from A to B and G goes from B to A. So I hope that answered your question as to what that would be doing.
So just to piggyback off of that, could we go over exercise 32.4, proving case 2?
Yeah, so let's see. So which one was that one? That is A2 is which one? Is that the one where it starts in A?
It's defining, let's see. Yeah, it's defining A2 to B2.
Yeah, I'm just trying to remember which one A2 is.
Oh, yeah.
Because that's going to be the thing that makes the difference.
The chain never loops and has an ultimate ancestor in A.
Okay. So that's the situation where it starts in A. So it has some like A naught, and then it goes to B, and it's just going to kind of go like this infinite chain from then on. So what we can do is we can list all of the different elements. So we can say A0 goes to some element B0, which then goes to some element A1, which then goes to some element B1, goes to A2, goes to B2, goes to A3, and so on. And we need to define a bijection from A to B. So what we can do is, if we define our function h going from A to B, let's just start by looking at, if we have some element A, send it to the very next thing in this chain. So A1 goes to B1, A2 goes to B2. So we're basically saying that h of A sub k is equal to B sub k. Now, the question is, how did we get those B's from our chain? So the way that we were going is, if we are traveling from A to B, that is using the function f. But if we're going backwards from B to A, then we're using the function g. So that tells us that we are basically saying that h of A is equal to f of A. We're just saying plug A into f and see where it goes. And so that's how we define our bijection on A2, specifically the places where it starts in A. It's starting in A, goes to the thing that it maps to under f in B. And so that's going to be what our bijection is. What's left is to prove it is actually a bijection. So it's injective because f is injective. The tricky part is to prove that it's surjective onto B2, which are these elements in B that had an ultimate ancestor in A. You have to prove that that means that it's going to be hit by something.
So before you go ahead and do it, if I can just try to put it in my own words. So
Yeah.
would we use like the argument for going backwards? Would we say, well, if we take an element of B and then it'll have a, what do they call that? A parent? Is that what it is?
Yeah, it'll
So
have a
like a
parent.
parent in A, and we can just keep going like that until we get back to the ancient ancestor in A. You know, like, and you can do it by contradiction maybe, like in a more, if you wanted to do it that way and say, well, assume that you don't, right?
Mhm.
And then that would mean that the ancient ancestor is in B, which would be a contradiction to your assumption. Like, is
Yes.
that like the...
Yeah,
Okay.
so assume there isn't an ancestor in A. Well, if there's no ancestor in A, then the first ancestor is in B, which would be your contradiction. So yeah, that would be a perfect way to say that means there is something that maps to it in A. And so then just take f of that element. So yeah, that's
Okay.
an absolutely valid proof.
Awesome.
Okay. Any other questions with this or other parts of 290? Let's see. Do you feel comfortable showing that two sets have different cardinalities, even if they're both infinite? You feel comfortable with injections and surjections and how those relate to cardinalities of sets?
So if I can just kind of talk through, so like to show that two sets don't have the same cardinality, there's a couple different ways to do it, right?
Mm-hmm.
Like one of them is to say, well, I can't find a bijection between the two. Or another way is to, let's see, okay, sorry, I'm just kind of thinking out loud. But so they don't have the same cardinality by showing there's not a bijection. Or, for example, we have theorems and saying like, okay, well, we know that this is countably infinite, or we know the cardinality of this, so if I can find a bijection from this to that, then like we've already shown that, say, like the cardinality of the natural numbers is less than the cardinality of R. So if I find like a bijection from one set to another, and I already know that two sets don't have the same cardinality, then that's like another way to do it, right?
Yeah, so if you can find that like one set, maybe A, it has the same cardinality as another set C, sorry. So if you show that A has the same cardinality as some other set C that you already know of, and you already have shown that the cardinality of C is not equal to the cardinality of B, that's another way to do it. So yeah, that's a perfectly valid way.
I can't think of any more off the top of my head.
Yeah, so a couple others are you can use like a Cantor diagonalization method. This is normally to show that this is something is not the same size as the cardinality of the natural numbers. So if you're trying to show that the real numbers are different size than the natural numbers, you could pretend that there is a bijection. So this would be a proof by contradiction. So you'd assume that there is a bijection, which would mean that you could list them. So once you list them, then you kind of go along the diagonal and have some way of changing every entry on the diagonal to construct a new element that is not in the list. And by doing that, because you had assumed there was a bijection with the natural numbers, that meant that everything had to be in that list. And so by finding anything that's not in the list, you get a contradiction. So that's the third way. And then another one is the Barber set can be used to show that a set has a different cardinality than its power set. So this is to show that the cardinality of A is not equal to the cardinality of the power set of A. So those are the situations that I can think of to be able to show that two sets have different cardinalities. Are there any of those that people would like to go over, or concepts that you're less familiar with involving these?
I mean, if no one else has anything, the Barber set, I have a vague idea. I kind of forgot about that, honestly.
Mm-hmm.
I also don't understand Cantor diagonalization.
Okay. Yeah, we can definitely go over both of those. So let's start with the diagonalization one, because the Barber set is sort of a extension of that method. So let's show that the cardinality of the interval from 0 to 1 is not equal to the cardinality of the natural numbers. So we would assume by way of contradiction that they are the same. So we've assumed that they are equal. And that's going to tell us that there exists a function f from the natural numbers to the interval 0 to 1, which is bijective. And so what that means is we can list every single one of our entries in, we can list every real number between 0 and 1 in a list. So we can have like a 0 point, maybe it's a 1, 2, 3, 1, 2, 3, 1, 1, 2, 3, 1, 1, 1, 2, 3, I don't know, some real number in some decimal notation. We have another one that's just a whole bunch of 8s, just on repeat forever. Like maybe we have that, maybe the next one is a whole bunch of 0s, but then there's a 1 and then a bunch of 0s. And then maybe we have, I don't know, something else, like maybe it's 1/10 of pi, so it's like 3, 1, 4, 1, 5, 9, 2, 6, and so on. So we have a whole bunch of these, and these are like f of 1, f of 2, f of 3, and so on. So we're assuming that we are able to list every single one because we have a bijection from the natural numbers to the interval 0 to 1. So anytime there's a bijection from the naturals to something, that means that you can list them. Cantor's diagonalization method says, now that you've listed everything, look at the diagonal entries. So we have these diagonal entries, and then we are going to change these and construct a new element that is not already listed. I apologize if any of you are colorblind because I'm using red and green, so I'm sorry about that. So let's do some sort of digit change function. So we are going to start, it has to start with a 0 point something. And our first decimal, we want to be different than the first digit in our first real number. So we just want it to not be a 1. So let's just change it to a 3. Okay, perfect. We've changed it to something that is not listed. Then we move to the next digit. We want the second digit to not be an 8. So let's just make it a 3 again. Like 8's not a 3, so we can just kind of go along this pattern to continue to make a different number that's not already listed. So let's say that our digit function says if not 3, it becomes 3. So if it is 3, make it a 7. So we just need to change it to something. It doesn't matter what we change it to. You could say if it's not a 6, change it to a 6. If it is a 6, make it a 2. That would be another perfectly valid digit change function. The only thing you have to be careful about with real numbers is to never be changing something to a 9. Because if you have 0.99999, that's equal to 1, which is not inside our range. And so that's something that you have to be careful about sometimes with this. But as long as you never change something to a 9 or a 0, because that would be the other problem, then you'll be perfectly fine. And so that's the diagonalization method. It's a way to construct something that is not listed in our range of f. So it's something that is not the output of some input in our function f. So this is telling us that f is not surjective, which contradicts our assumption that it was a bijection. Did that answer your question about the diagonalization method?
So if you can just make up like your list, because you're just listing random elements in between 0 and 1, why can't you list like 0.3333 and so on and so forth?
So that's a good question. Let's say that we were able to list it somewhere. So let's say that we had listed it right here at f of n. So f of n is equal to 0.3333 and whatever else is going on. So eventually we are going to have our nth digit. So let's say that, imagine it was a 3 in our nth spot. So this is at our nth position. Well, that means that our diagonal has now intersected with our f of n right there. So the rule says we are going to, if it showed up in the list, it's going to intersect with our diagonal somewhere. So that tells us that if at our nth spot it is not a 3, make it a 3. Well, 3 is 3, so we are going to have to change that to a 7. So that has to now be a 7, but now it's a 7 in the spot on our diagonal, which is not a 3, so we have to change it back to a 3, which means we have to change it back to a 7, so we have to change it back to a 3. So it's impossible for it to show up anywhere in our list. Because if it shows up in the list, it shows up at some finite position, which means it's going to have an intersection with the diagonal, which means we can't have any digit there, which doesn't work when we're dealing with real numbers. Did that answer your question as to why that shows that it doesn't show up in our function?
Yeah, thank you.
Yeah. And so the Barber set's going to do something very similar to this, except the Barber set is dealing with sets that might be uncountable. The only reason that the Cantor diagonalization theorem works is because we were dealing with a countable set, meaning that we were able to list every single element. We're not always able to list every single element. Like maybe we're trying to show that R has a different cardinality than the power set of R. We can't do the same argument. We can't do a diagonalization method because we can't list every element in the real numbers. And so that's why we need a different method of doing this, and that's where this the Barber set idea comes in. So the Barber set, B, this is the set of elements. So if we were, instead of dealing with R, we are dealing with the power set of some set A. So that is saying take all the elements x in A such that, and we are saying assume f is a bijection. Well, not necessarily a bijection. Assume f goes from A to the power set of A. So the Barber set for a specific function f, you usually don't have the subscript, but I'm going to put it there so that we know it's a set with respect to this function f, is the set of elements in A where x is not in its image. So that is how the Barber set's defined. Now, the way that we use this is if you assume that f is a bijection. Then that means that for every possible set in the power set of A, so every subset of A, there is some element that maps to that subset. So the question is, what element maps toward the Barber set? Is there able to be an element that can map to this Barber set under F? So the question is, what happens if there is an element that maps to the Barber set? So if we start by looking to see what would happen if, let's say that f of y is equal to the Barber set. Is y an element of the Barber set? Is it possible for y to be in the Barber set?
No.
No, because if y was if we did say that y was in there, then y is an element of the Barber set of f, which is equal to f of y. So that tells us that y is an element of its image, which tells us that y cannot be in f of y. But if y is not in its image, then y has to be in the Barber set, which means that we are going to keep running into the same sort of contradiction we were running into last time. If y is in the Barber set, then it can't be in the Barber set, but if it's not in the Barber set, then it has to be in the Barber set. And we're sort of going back and forth all the time with this, which tells us that the Barber set can't be in the image of f. We can't have any element that maps to the Barber set under this function f. And so that's able to prove that every set has a different cardinality than its power set, which actually tells us that it's impossible for there to be a set of all sets, because if there was, then it would have its power set as a subset, which would run into all sorts of these problems again. But I don't think that last comment will be on your test. Any other questions with the Barber set or with cardinalities? I know it can be confusing.
Can we do an example where we use the Barber set?
Yeah. So most of the time when you do the example, that is to prove that it's like the Barber set only gets used explicitly when you are proving that a power set has a different cardinality than its original set. But what you can do is you can say that if A is like the set containing 1, 2, 3, 4, and 5, and you say that F is, and you define what like F of 1, 2, 3, and 4, and 5 are, then you're able to then figure out what the Barber set would be. So if F of 1 is the empty set, F of 2 is A, F of 3 is the set containing 3 and 4, F of 4 is the set containing 1, 2, and 5, and then F of 5 is equal to the set 1, 3, 5. Then you can figure out what's the Barber set with respect to F. It's the set of elements that are not in its image. So let's just go through each element one at a time to figure out if it's in the image. So is 1 in the empty set? No. So 1 is going to be an element of the Barber set. But then is 2 an element of A? Yes. So that tells us that 2 is not going to be in the Barber set. So we skip that one. 3 shows up right there. So 3 is not in the Barber set. But 4 does not show up in its own image. So 4 is going to be in the Barber set. But then 5 shows up. So our Barber set is just the set 1 and 4, which is not any of the images of F. But then if we were to change it and like maybe make some of these sets different, then the Barber set might change. But the Barber set is always going to be a set that's not in the image of the function that generated it. Was that a good enough example for you, or would you like to do something else with it?
No, that was great. That was a great refresher. Thank you.
You're welcome. Any other questions that people have?
Could we do, I just saw this other question in exercise 32.3.
Mm-hmm.
Could we go over that one by chance?
Yeah, 32.3. Okay, so an injection from A to B and a surjection from A to B. Okay. So we have some set A, and we have another set B. So we have F is injective.
Oh, sorry, it's 32.3, or 32.2, sorry.
32.2? Okay.
Yeah, so proving 5, well, including 5 to 16 and then 0 to infinity have the same cardinalities.
Okay, so let's go and say that the first one is A and the second one is B. So what we want to do is we want to find an injection from A to B and an injection from 0 infinity to, or from B to A. So what would our function f from A to B, or f defined from 5 to 16 to 0 to infinity, what would an injection be that would work out nicely?
I did 17 minus x.
So that would be one that would work. We could also just say that our injection is f of x equals x. Just send everything to itself. That is going to be an injection from 5 to 16 to 0 to infinity, because 5 to 16 is a subset of 0 to infinity. So just sending everything to itself is going to be an injection. But your other function that you said, where you said it was like 17 minus x, that is also going to be an injection. So you could use that one too. So both of those would be valid injections, but we just need to have one injection. So saying f of x equals x as one injection from A to B, that's good enough for that half of our proof. The other thing we have is we have to have a function g that goes from B to A. So we have to have some function g that goes from 0 to infinity and then somehow shrinks that down to 5 to 16. Well, if we're dealing with numbers bigger than 1, 1 over x is always going to be smaller than 1, if x is bigger than 1. So that would be helpful. It would like shrink the 1 to infinity part down to just being this like interval from 0 to 1, which is definitely a smaller interval than 5 to 16, because we can easily fit an interval of length 1 in there. But the challenge is we have that 0 thing that we're dealing with. So let's just say that we are doing a 1 over 2 plus x, because then the denominator is always bigger than 2, So we're basically shrinking this down to an interval from 0 to 1, 0 to 1/2. The problem now is 0 to 1/2 is not inside 5 to 16. So let's just add enough to get it in there, but not too much that it then goes past it. So if we deal with g of x equals 1 over 2 plus x plus 8, we have this, basically this interval 0 to 1/2 is now an interval from 8 to 8.5, which is inside 5 to 16. And so that can be one example of an injection going the other way. It's definitely not the only one, because we could have changed the plus 8 to be a plus 6. We could have made it a plus 6 or a plus 11 or a plus 13.2. Any of those would have worked. We just needed to have one injection.
Can't you also prove that there's a surjection, like the function that you used as an injection? Injection is also a surjection, so there's a bijection and they're equal?
If you can find a bijection, then you can totally go with that. However, the challenge is to figure out what bijection works when you are dealing with a half-open interval here and a fully open interval on the other side. There are bijections that exist, and that's what the Schroder-Bernstein theorem tells us. If there is an injection from one to the other and an injection going the other way, then that means that there must exist a bijection. It just doesn't tell us what the bijection is. So if you can find the bijection, then that would work. But in this particular problem, we don't necessarily need to figure out what that bijection is, especially because half open to double open are a lot harder to find those specific bijections. They exist, but they're just hard to find. But you are right. If you find an injection that is also a surjection, then you don't have to find a second injection.
Can we talk about inverse relation?
An inverse relation?
Yeah. So here says things to know for exam 3. Definition of inverse relation and know when it is a function.
Yeah. So an inverse, so let's say that we have some relation R, and it's a set of ordered pairs. So we have like the pair A1, B1, the pair A2, B2, and so on. So we have some set of ordered pairs. The inverse relation is going to be the set of ordered pairs where the order gets switched. So it's going to be the pair B1, A1, then the pair B2, A2, and so on. So if R goes from A to B, then R inverse is going to go from B to A. So that's what an inverse relation is. To show it's a function, it has to then satisfy the two requirements for something to be a function. And those requirements are that f is a function if 1, for every, it's a function f from A to B, if for every element in your domain A, f of A exists. And 2, for every A in A, f of A is unique. So you would have to show that those two things are true for an inverse relation to be an inverse function. So if, for example, in your inverse relation, all of a sudden there's some element in your new domain that doesn't go to anything, then it's not going to be a function. And if there is something in your domain that goes to more than one thing, it's also not going to be a function. It has to satisfy both of these requirements for it to be a function.
You think that we can maybe like do like a quick proof about it?
Like an example?
Yeah.
Yeah. So let's say that we have f defined from the interval, let's see, f defined from the real numbers to the interval 0 to infinity, where f of x equals the square root, or equals x squared. So there is a function which is going to be a relation, because all functions are relations. So let's look to see what is f inverse. F inverse is going to be a relation from 0 to infinity to the real numbers. And now we have to figure out what are the elements in this relation. So if we were to graph this one first, it was going to look like that. The graph of this one is going to be this sort of curve, where it's going from 0 to infinity to any real number. And from the graph of the relation, you might be able to be guessing that this is not going to be a function. Because, for example, we have the pair, let's see, we have like 4, 2, and 4, -2. These are both elements in our inverse relation. So this is not going to be a function. It is a relation, but it's not a function. If we were to, instead of allowing any output, so we were to change our original domain to be the interval like 0 to infinity, so only taking the positive numbers, we would have eliminated that part of the graph. And so then that would then be unique. So we would have taken care of uniqueness. But then the problem is now we don't have 0, 0, which would be what it would be, is not in the inverse as well, because we have eliminated that as well when we made it the fully open interval. So in order to make it work, we would have had to have had f be defined from 0 to infinity to 0 to infinity in order for f inverse to be a function. Does that make sense?
Yeah, I think so. Yeah, well, we have to do the vertical test line, I guess.
Yeah, the vertical line test is a way to tell if it's well defined. So yeah, a function f is a well-defined relation that has an output for every input.
Okay. Can I ask another question? If no
Yeah.
one... Can we do the proof from the cardinality of the natural numbers to the cardinality of the integers?
We sure can.
Thank you.
Alright, so let's prove that the natural numbers have the same cardinality as the integers. So if we want to do this using Schroder-Bernstein, we just need to find an injection going both ways. But if we want to do this with a bijection, we need to figure out what bijection would work. So let's figure out how we might want to be splitting up the integers to figure out how we might want to try and define a bijection. Because we could try and do it directly and just have a function where a single input goes to a single output, which, well, that's what we want every function to do. But oftentimes with these, it's easiest to do them if we are doing a piecewise function.
I have a question.
Yeah.
Do we have to hit, like, for example, if it goes from the natural numbers to the integers, do we have to hit every natural number, right?
Yeah, we would have to use every natural number to hit every integer.
So wouldn't f of x equals x would be an easy one?
So f of x equals x is an injection. But it's not going to be a bijection because there's nothing that it, so there's no a such that f of a equals -2. So it would be injective, but it would not be surjective.
But aren't we just trying to find injection so that we can use the Schroder-Bernstein theorem?
Yeah, so if we're doing this and using the Schroder-Bernstein theorem, this would be a good function. So f defined from the natural numbers to the integers. But now we also need a function that's going to be defined from the integers to the natural numbers that is also an injection. So we also still have to find an injection from the integers to the natural numbers. So if you can find an injection going from the integers to the natural numbers, then you can use Schroder-Bernstein on this.
So like x squared plus 1?
X squared plus 1 is not an injection.
Should we use a piecewise function?
Yeah, so we'd have to probably do a piecewise function for this. And if we're doing a piecewise function for this injection, we might as well try and get a piecewise function to generate a bijection. But yes, you can use a piecewise function to get g from the integers to the natural numbers. So the way that I would do this one, and I would do this one with a bijection, is I would start by writing my integers into, because one way we can do it is to just list integers. So if we can list all integers, so we have like 0, 1, -1, 2, -2, 3, -3, 4, -4, and so on. If we're able to list everything, that is basically our bijection. So we have, this is f of 0, this is f of 1. Oh, does your book have 0 as a natural number? I always forget.
No,
Some
it
books-
doesn't.
Yours does not? Okay.
Not from what I remember.
Okay. Because there's two conventions. There's the European Convention and the American Convention. Some of the textbooks at the university use the European Convention, which has 0 as a natural number, and some have the American Convention, which 0 is not a natural number. So I always forget, because half my classes use one, half use the other. Alright, so we have f of 1, then f of 2, f of 3, and so on. And this defines a bijection. So you could list them and have this be your bijection, or you could try and come up with, how can I write this as a piecewise function? So you could have like f of x equals two situations. It could be x over 2 if x is even, or if x is odd, then we have to figure out how does 1 go to 0, 3 go to -1, 5 go to -2. Well, that's going to be a negative 1 minus x over 2. You might be wondering how I pulled that out of my hat so fast. It's because I've done this proof several times. I know what function to pick. If you didn't know what function to pick, you'd list them out and be like, okay, f of 1 goes to 0, f of 3 goes to -1, f of 5 to -2, and try and find the pattern and find a way to represent the pattern as a function. But this piecewise function is going to be a bijection from the natural numbers to the integers, and then you just have to prove that it is going to be a bijection.
Sorry, what was it that you did first? From 0, 1, -1, 2, -2?
So if you can list every element in the set that you're trying to show is equal to the same size as the natural numbers, if you can list all of those elements, then that list is going to be a bijection.
Okay. But can we do that? Not right.
If you just list them and then define your function that way, that is a valid way to do it. You just have to justify that you have actually listed every element. So that's actually how you prove that the natural numbers have the same size as the rational numbers. You find a clever way to list every rational number.
How does that cover the even negative numbers then?
So the even negative numbers come from like the, I don't know, maybe like the double odd numbers. So the numbers that can be written as like a 4k plus 1. So like 0, it's like f of 1, then you'd have f of 5, you'd have f of 9. Those are how you get those negative even numbers.
So isn't x's domain supposed to be from the natural numbers though?
Yeah. Sorry. This negative sign right there should be gone. So yeah, so if you're wanting to get like a negative natural number, so let's say we want to have f of x equal negative 12, for example. Because it's negative, it's going to be in this situation. So we are going to say that means we can figure out that we have a 1 minus x over 2 equals negative 12. So that means that 1 minus x equals negative 24. So 1 plus 24 equals x. So x equals 25 is a solution. So that's how you would get those negative even numbers. So any negative number is going to be represented by an odd number. Any positive number is going to be represented by an even number. Did that answer your question?
Yes, thank you.
Okay, so this is the, I guess, easier way to prove this proof. It's
So
by
this-
bijection.
Yeah, just finding a bijection is always a way that you can go about doing it. The times that I would not try and find a bijection is if the bijection looks like it would be really nasty. So like, for example, when you were having those like half open intervals going to this, maybe if there's a union in here, that might be pretty messy. So that would be a situation where I would want to try and use the Schroder-Bernstein theorem to try and deal with these kind of messy sets. Whenever the sets are fairly messy, it's often easier to do the Schroder-Bernstein theorem. But when you're dealing with sets like the natural numbers and the integers, it's often not too bad to find a bijection. However, you are always able to use the Schroder-Bernstein theorem. Does anyone have any other questions?
I have a question.
Yeah.
So proving two functions are equal, so in order to be equal, they need the same domain, codomain, and then rule.
Mm-hmm.
So how would you prove that? Like, say someone was to say, hey, prove that these two are the same. Like, is it enough to just say, look at their domain, look at their codomain, and then look at their rule? Like, or how would you prove it?
That's how I would go about it as well. So to show that like you have two functions f, like a function f equals a function g, yeah, check the domain and codomain. So you check that both of those are the same. So once you've checked that, then you check that for all things in your domain A, see does f of A equal g of A. And then if that's true, then you're done. Then they're the same function.
Okay, that makes sense.
Yeah, so that's how I would check it. Oftentimes those are sorts of things where there's multiple ways to get the same output. Often when you're dealing with like the integers mod n, there's more than one way to get to the same output. Because like in Z5, there's only, 25 different functions? Because you only have 5 choices of where to send everything. So there's only 25 functions in Z5. It's just a matter of which of all the infinite ways to write those are the same.
Can we prove if S and T are countable sets, then S union T is countable?
Yeah, we can do that. So S and T are both countable. So we kind of have a few different cases. Case 1, S and T are both finite, in which case S union T is finite. And we're done. If you have two finite sets, their union is still finite. Perfect. Finite sets are all countable. So that's that case dealt with. The second case is where S is finite, but T is countably infinite. In which case we have to find some way that we can list everything. Well, because S is finite, we can list all of them and we know it's going to stop. So we could say like S1, S2, through our nth element of S, at which point we stop. And then we have our infinite T elements, so T1, T2, ... to infinity. And here is a list of those elements, which tells us that this one is also going to be countable. Case 3 is where S is infinite and T is finite, which is the same thing as case 2. Just switch the S's and T's. And then the last case is where both are finite, both are infinite. In which case we can't list one set until we finish and then list the other one, because then we'll never list our second set. So here we have to alternate. So you have like S1, T1, S2, T2, S3, T3. And so by alternating and going back and forth that way, you're guaranteeing that you will hit everything. And so this list is going to be how you have your listing of it to show that it is going to be countable. So that would be the way that I would go about proving it. Maybe have a little bit more words to make it more formal of a proof. But that's the sketch of how you would go about the proof.
And that's just to prove that S union T is finite in all four cases?
So that's to show that S union T is countable. Not necessarily finite, but countable. So either finite or countably infinite.
I was asking this one because in the book they have like T prime equals T minus S, and then they have...
Yeah, the reason for that is they're being a little bit more careful than me. Because it's possible that maybe this element and this element are the same element. So they're just avoiding double counting. So what you could do is you could say list them, and if you come across a duplicate, skip it. But what they're doing is they're just being a bit more careful than me and saying that just drop any terms that get that are repeated. But I didn't deal with that case. So yeah, like each of these cases are slightly bigger. Just you have to deal with what do you do if you came across the same element again? And the answer is just skip it the second time. So that's what the book is referencing when it's saying like S prime, T prime. Yeah. Any other questions that people have?
Could we prove that the Cartesian product of the natural numbers is also countably infinite?
Yep.
Cool.
So we are looking at n cross n. So let's just write down these sorts of pairs that we're going to come across. So we have like 1, 1, 1, 2, 1, 3, 1, 4, so on. Then we have like 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3, and so on. And then we just kind of keep going along the same sort of pattern, infinitely far in every direction. So now what we have to do is we have to come up with an order. So we have to come up with some way to list them. And this is where the book references up arrow notation. So that's just saying draw an arrow that is representing the path that you're going to follow. So the book kind of goes like, go up like this, then go up like that, then go up like that. That's one possible way to be able to list it. Another one is to just kind of have this sort of swirly path where you're saying going here, and then when you finish a row or column, just kind of loop around. This is another perfectly valid path. As long as you hit everything exactly one time, that's going to provide a way to list or to order the elements, which is your bijection. So this first element is going to be, here's f of 1, then here's f of 2, f of 3, and so on. So I'm sure there's a clever way to write this as like a piecewise function, but I don't know what it is, so I'm not going to bother trying to figure it out. But being able to list them and have an ordering or a path that goes through all of them, that's a good enough way to be able to show that they are the same, that it is also going to be countable. And this is the same way that, that you can show that the rational numbers are countable, where you just skip anything that's a duplicate. So in place of these ordered pairs, you'd have like 1 over 1, 2 over 1, 3 over 1, 1 over 2, 2 over 2, 3 over 2, and so on. And then you just skip any element that was a duplicate. Any other questions that people have?
Would be something like that if we want to prove that the rational positive numbers are countably infinite?
Yeah. Yeah, that would be a way to be able to go about doing it. Yeah, you'd replace these ordered pairs with positive rational numbers, and then just anytime that you come across something that you've already done before, you just skip it. That would be a perfect proof that the positive rational numbers are countable.
Do you think that we can do it?
Yeah.
Thank you.
So if we go through and write down our positive rational numbers, so we have like 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. Then we have 2 over 1, 2 over 2, 3 over 2, 4 over 2, 5 over 2, and so on. We have 3 over 1, we have a 4 over 1. Let's see, we have, I messed up.
I think that you can start like 1 over 1, 2 over 1, 3 over 1, 4 over 1, or I don't know if it matters.
I just accidentally switched the way that I was listing them halfway through, so I had to go back and fix it. Alright, so yeah, so if we list all of these elements in these different ways that we got them, so let's see. Alright, so we have these listings, and the reason I'm writing some of these in red is because some of these are going to be duplicates. So if we are going in this order, using just up arrow notation, as we continue along these paths, some of these numbers are going to be numbers that we've already hit before. For example, 2 over 2 is just a fancy way of writing 1 over 1. So because we've already listed it before, it's not going to be listed again in our function. So we'd have 1 over 1 is like our f of 1, 2 over 1 would be f of 2, 1 over 2 is f of 3, 3 over 1 is f of 4, but then 2 over 2 is not f of 5. Because we've already hit it before, we skip it. So then 1 over 3 is going to be f of 5. And we have f of 6 down here, and we just skip any time that we've hit something that's already shown up earlier in our list. And so that's going to be how we are going to be defining our function. We skip anything that we've already hit before. So all of these numbers that I wrote in red are skipped. Did that answer your question?
Yeah, thank you. So is how pretty much you do the proof? Like you just show this?
Mm-hmm.
Of course, you put some words in the beginning and then on the end.
So you'd have a little bit of work saying why you're going to hit everything and how you know you're not going to hit anything twice. So you're going to hit everything, that's showing a surjection, it's a surjection, and you don't hit anything twice, that's to show us an injection. So once you've established that, this up arrow notation is going to be the way that you define your function. And so then once you have that, that's going to be the entirety of your proof.
So I just have like a thought with this.
Uh-huh.
When we look at these, I mean, when we do all these proofs and stuff like that, what we're really saying is the size of the irrationals, right? Like the irrationals are really huge because you have these, the irrationals, because you have the rationals, which are countable, but then you union that with the irrationals, then you get the reals, which is uncountable. So really what you're saying is that, well, what we're saying is like there are so many irrational numbers that they're way more than the rationals, which is kind of interesting. But like, I'm just kind of like thinking, because both the rationals and the irrational numbers are dense in R though.
Yeah.
Like that is crazy to think about, because you're like, oh, well, give me any two real numbers. I can find both a rational number between them and an irrational number between them. But yet the irrational numbers are way bigger than the rationals.
Mm-hmm.
Which kind of like blows my mind a little bit.
Yeah, there's a lot of cool ideas with cardinalities and sizes of sets with denseness. There's a lot of cool things that come about with having countable sets that are dense, especially when you're dealing with compactness, which is something that you cover in analysis and topology.
Yeah, closed and bounded.
Mm-hmm. Well, that's only in metric spaces. There's different definitions of compact, which one definition of compact is that there is a countable subcover for any open cover, which if you don't know what that means, don't worry about it. You have to take a topology class to get that. So don't worry if you have no idea what I'm saying right now, because that is not something that's on your test. But yeah, you are right. Both the rational numbers and the irrational numbers are dense in the real numbers. And that is one of those really interesting aspects of the way that we defined numbers. But yeah, it is cool. Does anyone have any other questions before we go off on weird tangents of other cool aspects of numbers and proofs? Go for it.
You know, we can keep proving some stuff.
Yeah.
So it would be the sorry. I'm trying to see. It's just that here it says know how to prove theorem 29.4, sorry. But I'm not sure how this one starts.
29.4.
29.4, yes.
The one I'm looking at doesn't have a theorem at 29.4.
Yeah, that's what I thought. Okay. Yeah, that it's kind of weird. I'm not sure. It's like an exercise, or I don't know what it is.
Yeah, I'm not seeing what that one is. I don't see what you'd have to prove with that.
Can we do 30.4 then? Which
The
says
proof of 30.4?
yeah, which says the set 0,1 is uncountable.
Oh, yeah. That's what we were doing earlier when we did the when we showed that the interval from 0 to 1 is equal to so when we showed it's not equal to the size of the natural numbers, because we know that the interval from 0 to 1 is infinite, and if we can show it's not countable, then it's uncountable.
Or will
Because-
we to use the like 1, 1, 0, 0, 0, whatever, and then keep going, and then say like, if it's 1, then it's 0. If it's 0, then it's 1, and then you create a new set,
Yeah.
a new element.
Yep. Yep. You would use a Cantor's diagonalization method to get that. Yeah, that's
Could you-
absolutely right.
Just as another way, could you also use like tangent to find that it's the same cardinality as the reals? Like,
Yeah.
I don't know, what would it be? Like tangent of n pi plus pi over 2 or something like that?
Yeah, so tangent is defined from negative pi halves to pi halves to the interval negative infinity to infinity. So if you can modify this interval to make it work, then yeah, so if you defined f of x to be equal to tangent of, let's see, because x is from 0 to 1.
it pi x plus pi over 2 or something like that?
It'd be, so let's see, so pi x would then mean that pi x is between pi and 0, so it'd be a pi x minus pi halves. So that would be your function that you would use. So pi x minus pi halves, or tangent of pi times x minus 1 over 2. Something like that. I'd stick with the top one. But yeah, that would be a bijection that you could use to show that it has the same cardinality as the real numbers, and the real numbers are uncountable.
Awesome.
But yeah, usually the order goes the other way around. The way that we prove the real numbers are uncountable is using the interval 0 to 1. But yes, you are right that you can use that bijection to show that it has the same cardinality as the real numbers. Any other questions that people have?
So could you explain this one again with the tangent?
Yeah, so this is a bijection from the interval 0, 1 to the real numbers. The way that we constructed it was using the fact that we knew that tangent went from negative pi halves to pi halves to the real numbers, and so we had to modify the inside of tangent to make it work on the interval 0 to 1. So because x can go from 0 to 1, pi x is going to go from 0 to pi, but we want it to go from negative pi halves to pi halves, so a negative pi halves is less than or equal to pi x minus pi halves, which is less than or equal to pi halves. So we just modified tangent, which was a function that almost did what we wanted, to then turn it into a function that did exactly what we wanted. Any other questions?
This is like a general question.
Mm-hmm.
So if you have a function, okay, doesn't matter what it is, as long as it's a function, it doesn't have to be injective or surjective. In general, like if you take, a surjective reduction of the function, right? And then, so now you have a surjection, or
So that's where
basically,
you do f restricted to the image of f?
yeah.
Uh-huh.
And so is it possible to like modify your domain and codomain to always get a bijection from some function, or is it not always the case? Because like we can always do like a surjective reduction, but I was wondering if we can also, if it's even possible at times for functions to do like also change the domain to make it injective and surjective, or
Yes, that is something that you are also able to do.
okay.
And the reason for that is you could basically just restrict f to a single point, which is going to always make it bijection, and then you can just slowly add points while keeping it a bijection.
Okay, that makes sense. Yeah, because I felt like it'd be good to know how to at least do surjective reduction, which is like what we do, but also
Yeah, the only thing with that is you have to decide how do you restrict it. Because you are able to restrict it. The question just then becomes like, if I have two inputs that give the same output, does it matter which one I restrict it to exclude? And that's where like the axiom of choice is going to come in. And that's why we all like the axiom of choice, because it makes us be able to choose things. But yeah, you are able to restrict it that way. Yeah, go ahead.
Oh no, I was just gonna say thank you. That makes sense.
Yeah, if you have any other questions, feel free to ask. I'll still be here for another few minutes. By few, I mean 20.
Can we prove theorem 31.5?
31.5. That is, that S, cardinality of S is less than the cardinality of the power set of S?
Yeah.
Yeah, so this is what we were doing earlier when we were showing that the Barber set, so where the Barber set is never in the image of itself. So you'd start by assuming by way of contradiction. So assume by way of contradiction that there exists a bijection F. So that means that, or technically just a surjection. No. Yeah, so you assume there is a bijection F, and then that means that for every set, what should I call it? So let's see. So that means that for every set in the power set of S, there exists some element in the set S such that f of x equals that element E, which is actually a subset of S. Because it's an element of the power set, it's a subset of S. So if we define B to be equal to the set of elements in S such that f of x is not in S. This is a subset of S, which implies that B is an element of the power set of S. So, because we have a bijection, that means there exists some element that maps to B. So, what that tells us is if we go through and figure out what that tells us, we now have f of some element y equals B. So the question is, y in B? So we kind of have two cases. If y is in B, then y is an element of f of y, which tells us that y is not in B, which is a contradiction, because you can't be both in B and not in B. So that tells us that y can't be in B. But if y is not in B, then that tells us that y is not in f of y, which tells us that y is in B, by the way that we defined the Barber set. And so because this set can never be in the image of f, which means that our function f was not a surjection, which tells us that the cardinality of S is not equal to the cardinality of the power set of S. And then you just have to show that there is an injection, which tells us that it's less than or equal to, which tells us that the cardinality of S is strictly less than the power set of S. And so that's why the Barber set is so powerful.
Thank you.
You're welcome. If you need more help with the Barber set, I do have a video on my channel that's like a 20-minute video explaining the Barber set.
I want to understand more 26.20.
2620. Let's see. Okay. Are there any of the particular ones that you want to do where like you have, so f is a bijection, which says that f inverse equals f. F inverse is a bijection. F inverse of f is the identity on A, and f of f inverse is the identity on B.
What did identity mean?
So this is the function g where g of x equals x for all x in A. So it's the identity function on A. So it's the function that sends everything in A to itself.
Oh, got it.
So f inverse of f just basically does nothing, so it's just a function from A to A that sends everything to itself. So that's what the identity ID sub A means.
So is it kind of like a relation?
So it is a relation, and then you're just proving that it's not only a relation, but this specific function.
Do you think that we can prove, can we prove that one?
This third one?
Mm-hmm.
Yeah.
Okay.
So we have f is a function from A to B, where f is a bijection. So let's see. So we have f inverse of f. So let's just look to see what does that do for an element A in A. So that's going to be equal to f inverse of f of A. Well, f of A is equal to some element in the codomain, but then f inverse, so if we have the A comma B is in F, then that means that B comma A is in F inverse. So it's in the inverse relation, which in this case is an inverse function. So that means that we are dealing with F inverse of B, which is equal to A. So
Okay.
the reason for that was we have the pair A comma F of A is an element of F, which means that F of A comma A is an element of F inverse. And so this is the wording that the book uses. So because A comma F of A is in F, F of A comma A is in F inverse. And so we're dealing with F of A goes to what in F inverse? Well, it goes to A, and so that's where we're getting that A out of. And so it's the identity on A.
So I'm trying to put this together with the definition that you gave me before, where you said like for all A
Yeah, so what we have is, so this right here is saying that for all the A's in our set A, F inverse of F of A is equal to A. So it always gives the same output as the identity. The only thing that we have left is to show it has the same domain and codomain. So F inverse of F, well, it goes from A to B and then back to A, so it's just a function from A to A. So it has the same domain and the same codomain, and it matches the same output every time.
Okay. Okay, thank you.
You're welcome. Did that answer all of your questions?
Yeah.
Okay.
Thank you, Mike.
You're welcome. Good luck. I hope this test review was helpful to you and that it was a good use of your time. I hope that you do well on any of your tests, and good luck with the rest of your math.